All right, starting a little late today. Sorry about that, guys. If you're eagerly expecting my stream on this Friday afternoon on the East Coast. Um, and I had started working on this sum of multiples exercise on exercism.io. It's pretty simple. Given a number, find the sum of all the unique multiples of particular numbers up to, but not including that number. And they give us an example here. So if we've got a maximum number of 20, and we're looking at multiples of 3 and 5, then we'd have 3, 5, 6, 9, 10, 12, 15, and 18. The sum of these would be 78. And I passed a few of the first tests up until 100, and I realized the problem was I was just storing the multiples in an array, and I had duplicates, right? They have to be unique multiples. So instead of using an array, I am switching to a set, which doesn't allow duplicates, and simply changing that to, isn't it set? What is it? Set, add. There we go, add to this. Now, of course, we're going to have to get back to an array if we want to use reduce to get the sum. Because although, let's just check this here, what's available to us. There is a for each, but we would need to implement our own thing there, our own reduce, which I'm not really keen on doing. When I can just do something like this instead. Watch this. That is the beauty of the spread operator. There we go. And now we've got the right result, 2318, 2318. So I can just comment that out for now. Keep going with my tests. There we go. Okay. One more. Actually, I don't see why I went past all of them now. So let's just go crazy and open it up. There we go. Simple as that. Don't need you anymore. Now, should we refactor? We've got this. This is a little cramped. Maybe like this. It's a little better. Multiples, nums for each. And we need the number here, so maybe do this like that. This thing a little bit more readable. Yeah. And then we could I gotta be right back, guys. And we're back. Okay, so yeah, just maybe a little bit of refactoring here, and this would be good. So we've got two loops, right, going on here. Is there another way to do this that wouldn't involve two loops? I don't see how, really. I could use a while loop here instead of the for loop I'm using, right? With my clever to infinity thing and breaking. I could store the I in a variable outside the while loop, then check that I isn't bigger. I could have this check here in the while loop. Might save. Let's see what that would look like just for fun. So I would have let I equals 1 on this line. Then I would have while I is, oh no, it's not I, it's the multiple that I need to check. And the multiple, I would get it inside. So I could do break though. So I could simply have true. I still have to store the I here though. Okay, let's try this. Then I just have true. And then I do I do this here. So there's not much that changes. And I actually have to do, once I'm done that, an I plus plus. So it's not like, let's see, we've got 1, 2, 3, 4, 5, 6, 7, 8 lines. 9 if you include the closing brace here. And 1, 2, 3, 4, 5, 6, 7. So yeah, nope. No reason to switch for that. Infinity multiple n times I, if multiples figure a num break. Multiples that add multiple. Yeah, that's what I'm going with. There we go. Solve sum of sim. Sum of multiples. Like that. Just make sure I didn't break anything. Good. Then I'll just submit that to Exercism. So submit, okay, just a file here, sum of multiples.ts. Make sure this worked. And it did. Yay. All right. On to the next one. That was this one. Let's try grains. Grains. Calculate the number of grains of wheat on a chessboard. What? Given that the number on each square doubles. There once was a wise servant who saved the life of a prince. The king promised to pay whatever the servant could dream up, knowing that the king loved chess. The servant told the king he would like to have grains of wheat. One grain on the first square of a chessboard, with the number of grains doubling on each successive square, and there are 64 squares, right? 8 by 8 on a chessboard, I think. Oh, there you go. There are 64 squares on a chessboard, where square 1 has 1 grain, square 2 has 2 grains, and so on. Write code that shows how many grains were on a given square and the total number of grains on the chessboard. Ah, that's pretty cool. Okay, 4 bonus points. Did you get the test passing and the code clean? If you want to, these are some additional things you could try. Optimize for speed. Optimize for readability. I like it. Then please share your thoughts in a comment on the submission. Did this experiment make the code better, worse? Did you learn anything from it? Okay, I like this. All right, so download this. So maybe do two iterations. One that cares about readability, the other one about speed, or the best of both worlds. We'll see. How exciting. Okay, let's get out of here. Yep, and then download. Good. And then grains, as simple as that. Yeah, okay. Print this. All right, grains. Okay, first let's commit that. Add grains. Exercise. Like this. Okay. All right. Default import as usual. And we are calling a static function on that grains class. Looks like. So let's set that up. Not expect, export. Default grain class grains. Boom. Static. What's going to be the name here? Square. Simple as that. Square. I think we're going to have more than one function though. We're probably going to have square and sum. No? Total. Total. There's just one test for the total. Interesting. Square, 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 square. And total. Static. Total. Total. Both of these are expecting a number as a return. And what else? What happened to our music? There we go. Beta. Okay, and square expects a number. Let's call it a square. Nah. That wouldn't work, right? So just QR, just QR number, maybe. Yeah, let's go with that. Return SQR num. Return 0. Good, so now that works for the compiler. Whoops, that's not what I wanted to do. That's what I wanted to do. And we're actually passing the test because it's probably just square one. Yeah, square one has 1, so. All right, so let's go ahead with square 2. See if we pass that. And we do. Yeah, because square 2 is 2. So far, so good. And this is where this shouldn't work, right? Square 3 should be 4 because it doubles every time. Now, what would be the most performant way of doing this? Well, let's just solve it and then optimize afterwards. So let's see. All right, I'm back. Let's see. Somehow it screws up with my music. And we've got to have some music. Let's see if I can fix this. Oh well. Looks like we won't have some music for the rest of the stream. That is unfortunate. I don't see why it would kill my music when I go to... Oh, let's see. And that's stopped it. Interesting. Okay, well, so I think as long as you hear it, good. Let's keep going. Okay. Yes, yes, yes. It doubles every time. So we're interested to know what's the math formula for that. If we're on square 1, we have 1, right? We're on square 2, this doubles. If we're on square 3, then it becomes 4. On 4, it's 16, etc., etc., etc. Now, I knew there's a math formula. 32. There's got to be a math formula. For this. I mean, one very straightforward way to do it is to simply, oh, wait a minute. Wait a minute. 1, 2, 4, 16, 32. We're dealing with something that looks a lot like binary, aren't we? Aren't we? Huh. Well, first, before I go playing with binary stuff, my idea was just to simply go and let's see, we could probably do this, right? Total number, and just use recursion. And this would equal 0 to start with. And then we would go return. Okay, so once if, that's our exit, it wants square num is equal to 64. Then return the total. But until you get there, just call yourself grains.square. Square number being 1 bigger. And taking the total and just doubling it. Simple as that. Need to return this like that. And that would do it. It's very simple, but probably not all of that performant. And apparently it doesn't even work. Whoa. Maximum call stack size exceeded. Yeah, no, I don't think so. What did I do wrong? If square num is equal to 64. We're calling the square number, oh, that we're interested in. Right, silly me. So this actually has to be the opposite. We're going down to 0. going down to 0. And we're taking the total. The total starts at 0. It shouldn't start at 0. It should start at 1. Right? So if it starts at 1, square number is 1. If it's 0, it's not 0, then square number is a total of 2. So no, that's not right. We should decrement the square number right here. Like that. And then just square num. Let's try this, see how that works. Ah, there we go. There we go. And let's open up our test suite, because I'm pretty sure we'll be good for square 0 raises an exception. Okay, let's wait and make sure that all these pass first. Good. Now square 0 raises an exception. What kind of exception? You don't even care. Cool. As long as it throws. And it does throw. Do you know why? Because we probably get a stack overflow. So it's negative square raises an exception. See what happens there. It does too. Square greater than 64 raises an exception. Now that is not gonna work. We're going to get an answer from that. Yeah. Right. Returns the number. Expect function to throw undefined. Expected the function to throw an error, but it didn't throw. So we need to check first that if square num is bigger than 64, we want to throw. And what are we throwing? We don't even care, but let's be smart and say throw a chessboard only has 64 squares. Let's run this. We're good. Now, total. Well, that's really easy. Because, all we really need to do is call our square. So, grains. Oh no. Oh yeah. Yeah. That's all we really need to do, isn't it? Square with the number 64. And that should work. I'm not returning it though. That could be a problem. Well. That's the total of every square I get ya. I get ya. So then the smart thing to do is, and that's probably going to be a killer for performance. Wow. It'll be fun to play with this afterwards. So, okay. I equals 0. As long as I is, and actually let's start it at 1. And then as long as I is smaller or equal to 64, we keep going, we increment this, we do that, we Control X. Well, actually, there would be a smart way to do this without having to loop over everything again. We're already doing that work in our square function. So why don't we do okay, let's call this square value, and let's call this total. Number is equal to 0. Where do I have the total? This is going to be square value. Now I'm going to have to store this here. We're going to go square value equals square value equals times 2, time equals 2, time equals 2. Okay. Then you just do square value, and then we take our total, and the total is plus equal. Yeah, plus equal square value. And then that allows us to simply call this here grains dot square, and we go 64. Yeah, how do I get the total out of there though? Aha. Yeah. Well, I guess I just need 2 versions of it. Right. If I'm calling, how can I get this out of them? I'm returning, oh, this should be the square value. Square value. There's no way to reach out and get this out of there. So basically, this can just be a copy of this. Copy of this. Basically, right? Except that now I will be returning oh, that's a problem. No, once we get to the very end, we're interested in the total. Is that gonna, no, that's not gonna work. Or is it? Let's think about this. So I'm starting at 64. So actually I don't need to store the square number here. Well, I could just do this. And I'm going down every iteration. Reduced by 1. So if I was at square 1, right, square value would be 1, the total would be 0, square 1, reduced by 1, boom, total 0, we're done. If I'm at square 2, reduced by 1, the square value is now times 2, so square value is now 2. I return grains dot square, so square num. I guess I don't care about the square value at that point, or do I? No, that's not going to work. That's not going to work. Yeah. Not going to work. Got to rethink this. Well, I do know a way. Right, I do know a way to make this work. It is not pretty, but I do know a way to make this work. It is not performant. Let's do it. So let I equals 1. I is smaller or equal to 64. I plus plus. So for each board, each square on the board, we call grains dot square with the I. Ugh. And we need some total. It's going to be 0. This will be a let. And then total plus equal grains square. And just return a total. And that'll be it. This will work, but will be super slow. Yay. Okay, so the current implementation works. We're passing all the tests. It's pretty clean, if you ask me. Right? Uses recursion, which obviously is not the, well, in JavaScript anyways, is not the most performant solution, I'm told. Now, can we clean this up a little bit more? Can we clean this up? Square number, square value equals 1. If square's number, chessboard only has 64 squares. Square num. Let's do this. If square number is equal to 0, we're done. Return the square value. Otherwise, square value, actually, now I don't need this here anymore, so let's make this like that. I don't need this in brackets. Square value times equals 2. I like it. I like it. I don't think there's any reason to change anything there. In terms of readability. Total. We start with a total of 0. Right? We loop for 64 turns, adding to the total. Greens.square I. There's another way to do this. Using a let's see, return array 64, so array.length, and then we reduce P and C. We do that, and we start it at 0. And here we go grains. So we actually need the index as well. Grains. Dot square. The square number is I. And we just go P dot grains dot square. We don't care about the C. I'm pretty sure that would work too. It's a nice little one-liner. Is it more understandable though? Might be. Is it more performant? Heck no. Let's see, just make sure we pass the tests with this. declared but its value is never read. Yeah. Got a problem with that? Here, take this. Received 0. Interesting. Interesting. Let's see what Quokka has to say about this. Oh yeah, I think I know. Yeah, I know what's going on. That's because the array, like, when you construct it, yeah, it has a length of 64, but what if I do this? I don't think it'll change anything, but let's try it anyways. Maximum call stack size exceeded. How can that be? If I do this, same thing. Wait. I gotta see this. Yep. How interesting. But if we just do it like that, then it's fine. It just doesn't give us the right thing, but And what if we go array dot from no, that won't work as well. Let's just do array 64. Let's see, let's experiment with that here. I'm not too sure. If I go array 64, what am I getting? I'm getting an array of 64 somethings that are empty. And if I call reduce on that thing, or let's say just a map x, and turn x into a1. Interesting. So as you can see, that didn't do jack. Very interesting. Why would that? Now if I did, let's say I did like this. Now that works. But for some reason, I'm exceeding the call stack when I do it that way. That's very interesting. Let's get rid of this here. And that's probably because we're using some sort of function. It's, yeah. Well, no matter what the reason is, fact of the matter is we're exceeding the call stack, so let's try not to do that. So looks like that's the implementation that we're going to go with in terms of the non-optimized solution. So we're going to save that. Solve grains, non-optimized. I should probably do a little bit of benchmarking here. So let's maybe let's get rid of this here. Actually, we could probably use Quokka for this. If I am to do well, the biggest one would be this one here, right? 64. So let's try this. If I do green dot square 64, and I do that, that gives me the answer. But if I want, how do I get the is that the way? Maybe. No, another one like this, maybe. Come on, Quokka. What's the secret here? Quokka JS. I'm looking at docs. Okay, maybe. Live feedback, logging, value explorer, blah, 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 blah. Live comments, that's nice. Live value, copy value, glue, glue, glue. Come on. Live performance testing. That's what we're looking for. Oh, there was a dot. I was missing the dot. Star, question mark, dot, star. So if I go star, question mark, dot, star, and this. Boom. Okay, but that's, what is that? It ran it just once, it ran it many times. What am I supposed to make of this? What if I was to just delete it to 0.46? Oops. Was it star, question mark, dot, star, 0.49, 0.47. I think it just runs at once. Which, you know, gives us a baseline. It's pretty much what we're getting every time, right? 0.45. Whoa, what happened there? Hmm. 0.45. Yeah, it's always around 0.047 milliseconds. All right. Let's see if we could do better. Let's see if we, let's see the total one though, just for kicks. Total, quite a bit longer. Shouldn't have anything in there. Yep. Well, let's try first to optimize our square function. By doing that, we'll automatically optimize our total function. Now, we're doing recursion. Well, I mean, 0.45 milliseconds is not that bad. Wait, how much was the total? Was that in millisecond as well, or? Yeah. We're talking pretty fast here. I mean, I don't know why I would want to optimize this, really, but optimize for speed, optimize for readability. I think this is pretty readable. I mean, I don't see how more readable it could be. This one here, anyways. Although it's never the easiest thing to figure out what's going on in a recursive function, especially if you're not familiar with them. But still. Okay, let me go ahead and just make a copy of this. And just put it here. Comment it out. Like that. And we can just see. Let's think about this here for a second. We get to could we use some kind of bitwise operation on this here? Left shift is like I wrote a blog article on this not too long ago. Let's go check it out. So bitwise shifting any number x to the left by y bits yields x times 2 to the y. So bitwise shifting any number x to the left by y bits yields x times 2 to the y. So if we wanted to looking at this here, we've got, would that make sense if we so 5 to the x times 2 to the y. X times 2 to the y is what we're interested here. X times 2 to the y is the equivalent of bit shifting any number x. Any number x to the left by y bits is the equivalent of x times 2 to the y, yeah. So can we use that? Well, let's clean this up first. So we know if our number x hmm, 64 times. No, hold on. Why don't we take a look, see what the Google has to say about this. Using bit operators to double, how do you describe something that keeps doubling? Bit operator to double, no, 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 no. Number keeps doubling bitwise. Okay, how to multiply given number by 2. Number can be multiplied by 2 by using this is done by using the left shift operator, yes. And shifting the bits left by 1. Yes. Okay, we know that much. Is it faster? No, it's not. And we can prove that quite easily, just for kicks here. Let's get our let's get back here. Okay. So instead of doing this here, we'll just bitwise operation, bit shift that left for 1. And as we can see, let's do this again. Yep, longer. Let's try it again. Yep. We had 0.45, 46, 47, and now we're at 0.52, 0.50. It's a bit longer. Doing it that way. Just gotta redo this here. I don't know. Not much of a difference. Now I'm up to 50 something now with this solution. All right. So just doing that doesn't really make a difference. But, whoa, got rid of too much stuff here. Just wanted this. Okay. Let's keep looking. Number. How to express a number that keeps doubling. I know there's a math formula for this. I know there is. I just can't remember what it is. I think if you want something to double a certain amount of time, I'm pretty sure there's a math formula for it where you don't have to actually go through the trouble of doubling it for a certain amount of X amount of time. So let's see if we can figure this out. Math formula, number doubles X amount of times. Doubling pennies, that's pretty much it. That's what we're doing here. 2 times 2 times 2 equals 8. 4 times 4. So y to the x means to multiply y by itself, x times. So if you want to calculate 2 to the 10, which is 10 factors, your calculations give you a way of thinking about it. Oh, could it be that simple? Really? Could it really be that simple? I am a dummy, if that's all we need to do. And I think it might be. So we start with 1 to the power of whatever the square number is. And then we return that. Could it really be that? Yeah, I think it might be. No, it's not, apparently. Oh, right. Obviously. Because that's like 1 to the power. Wait, hold on. So what are we saying here? 4 to the power of 2, 2 to the... But that won't work with 1. So on day 1, you have 1 penny. On day 2, you have 1 penny plus 2. It's 3 pennies. What? What is the penny problem? I had to start with a penny, double it daily for 30 days, and know the total number. Oh yeah, okay, so this would work here. Instead of doing... Okay, so let's bring back... No, I still win though. On day 1, you have 1 penny. On day 2, you have 1 penny plus 2 pennies. Yes, notice that this is 1 less than 4 pennies, and 4 pennies is 2 to 2. So on day 3, on day 4, yeah. Pattern here is very strong. We can confidently say that on day 30, you will have 1 less than 2 to the 30 penny. He says, minus 1 equals this. Okay. Okay. So that means that we can make this much faster. Let's take this. Star this dot no, this is a star. Like that. 1.184 milliseconds. 1.1. 1.29. Okay, well, we get the idea. Now if we were just to do return to the power of 64 minus 1. Way faster. And if that's the... Yeah, that's the correct answer. So that's cool. Much, 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 much faster. Kind of magic though. But, you know. Now, is there a way to use this for this here? Where we're not actually trying to get the total. We're just trying to get what we're at for that square. Notice that this is 1 less than 4. Notice that this is 1 less than 8 pennies, and 8 pennies is 2 to the 3. Cumulative math. A formula number doubles X amount of times. How many grains were on a given square? "64 squares on the board, where square 1 has 1 grain, square 2 has 2 grains. Exponential, yeah, it's exponential, that's right. So what we're trying to do here is get the next one would be 4. I need to double it daily for 30 days and know the total number for the month. I came up with 1 plus 1 equals 2 plus 2 plus 2 equals 4. Then added them all up. Geez, that must have been... So the equation to use is 0.05 times 2 to the x, yeah. Let's see here. If I do this, that is probably not going to be right. Right, because that gives me a running total. value to equal that, but received this instead. From the beginning. Expected value to equal 2, but received 3, yeah. It's the running total. But what if we get the running total and divide it by 2? I think that would work. Don't ask me why. I just see a pattern. Nope. Wait, what? How did that not change anything? Expect. Ah, crap. Didn't change the right thing. This is what I needed to change. Okay. Aha. Aha. Uh, 2 to the 64 minus 1. What does that give us? 1844, blah, 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 blah. Yeah, that's correct. Okay. Performance-wise, much faster. Now what if we tried this one? Yep, about half the time. No, actually much less than half the time. But for now, let's just fix what would happen if didn't throw. That's interesting. So let's try this. If we do square 0, what do we get? I can just do this, right? Yep. Get 0.5. That's interesting. So if square, if square num is equal to 0, or square num is bigger than 64. So is, we're going to use here, is smaller or equal to 0. Or square num is bigger than 64. Then just throw, and we'll throw something that says square is out of range on a chessboard. Let's try that. Oh. Error square test suite. Failed to, oh, because of this here, of course. One passed. Come on in. Faut passer à la télé. Ah, je finis de toute façon, là. That's my bro. Say hi to the world. Cool. All right. So I think that's it for me. We are good. I don't think we can get much more optimized than this. Maybe bitwise operation, but I'm not sure. JavaScript, they tend to be not really faster. I'll have to think about it, but I think this is pretty good. So thanks for watching. See you next week.